Title: XHand. Real-time expressive hand avatar. Abstract. This paper introduces XHand, a real-time expressive hand avatar designed to generate hand shape, appearance, and deformations in real time. The method utilizes three feature embedding modules to predict hand deformation displacements, albedo, and linear blending skinning weights. A mesh-based neural renderer is employed to achieve photorealistic hand rendering on fine-grained meshes. The proposed part-aware Laplace smoothing strategy effectively maintains the necessary details and eliminates the undesired artifacts. Experimental evaluations on InterHand2.6M and DeepHandMesh datasets demonstrate the efficacy of XHand, which is able to recover high-fidelity geometry and texture for hand animations across diverse poses in real time. Introduction. Hand avatars play a pivotal role in various digital interfaces, enhancing user immersion and facilitating natural interaction within virtual environments. While previous studies have focused on photorealistic hand rendering, little attention has been paid to reconstruct the hand geometry with fine details, which is essential to rendering quality. In the realms of extended reality and gaming, on-the-fly rendering becomes imperative. To this end, we introduce an expressive hand avatar, named XHand, that is designed to comprehensively generate hand shape, appearance, and deformations in real time. To obtain fine-grained hand meshes, we make use of three feature embedding modules to predict hand deformation displacements, albedo, and linear blending skinning weights, respectively. To achieve photorealistic hand rendering on fine-grained meshes, our method employs a mesh-based neural renderer by leveraging mesh topological consistency and latent codes from embedding modules. During training, a part-aware Laplace smoothing strategy is proposed by incorporating the distinct levels of regularization to effectively maintain the necessary details and eliminate the undesired artifacts. The experimental evaluations on InterHand2.6M and DeepHandMesh datasets demonstrate the efficacy of XHand, which is able to recover high-fidelity geometry and texture for hand animations across diverse poses in real time. To reproduce our results, we will make the full implementation publicly available at https://github.com/agnuson/xhand. The existing methods for hand modeling and rendering have limitations in capturing the geometric details and photorealistic images of hands. To address this, the proposed XHand approach aims to simultaneously synthesize detailed geometry and photorealistic images for drivable hands. This is achieved through a neural hand representation that combines feature embedding modules with mesh-based neural rendering. The XHand method employs a parametric hand model, mono, to initialize the hand geometry, which maps the pose parameter theta and shape parameter beta onto a template mesh. The posed hand mesh is then refined using a personalized vertex displacement field, allowing for extra deformation for each vertex in the template mesh. The refined mesh is computed using linear blending skinning with the weights W, and the geometry refinement is enhanced through an uniform subdivision strategy on the mono template mesh. The feature embedding modules, Psi-D and Psi-LBS, are designed to capture the intricate details of hand mesh and LBS weights. These modules rely on the average features of hand mesh and compute offsets of features in different poses. The feature embedding module extracts mesh features Fm as a function of the pose theta t and the average vertex features of hand mesh Fm. The embedding function psi, theta t, Fm, combines a pose decoder with multilayer perceptrons, MLPs, to project the pose theta t and latent code q onto the implicit space. The XHand approach is compared to existing methods, including Hand Avatar, Hand NARF, LISA, and Live Hand, which have limitations in capturing the details of hand mesh geometry. The proposed method is able to synthesize the hand avatars with fine-grained geometry in real time, making it suitable for applications such as virtual reality and computer-aided design. The method is evaluated using multi-view images and hand pose parameters, and the results show that XHand can generate both detailed geometry and realistic rendering in real time. The feature embedding modules are able to capture the intricate details of hand mesh, and the mesh-based neural rendering achieves photorealistic renderings. The XHand approach has the potential to be applied to other animatable objects, such as human bodies and animals, and can be used in various applications that require realistic and detailed hand modeling. The proposed feature embedding module, as depicted in Fig. 4, enables the interpretable acquisition of hand features corresponding to the pose θ-t. The module consists of three different feature embedding modules, Psi-LBS, Psi-d, and PSR, which predict LBS weights W, displacements d, and albedo ρ, respectively. The personalized mesh features Fm are derived by combining the average vertex features Fm and the pose-dependent offsets. The LBS weights W are obtained using the pose decoder Phi-LBS, latent code QLBs, and mapping matrix KLBs. Similarly, the vertex displacements dt are obtained using the pose decoder Phi-d, latent code QD, and mapping matrix KD. The feature embedding modules allow for the simplification of training objectives by taking into account the average features constraints, leading to faster convergence and improved accuracy. The mesh rendering process involves inverse rendering, which synthesizes hand images using the spherical harmonics coefficients g, vertex normal n, and vertex albedo ρ. The pose-dependent albedo ρt is obtained from the feature embedding module PSR with average vertex albedo f ρ, pose decoder fr, latent code q ρ, and mapping matrix k ρ. The mesh-based neural rendering method is employed to minimize sampling time and enhance rendering quality. The mesh is explicitly represented by triangular facets, and the features that describe meshes, such as position, color, and normal, are associated with their respective vertices. The neural renderer C synthesizes the image with respect to the position x, normal n, feature vector hand ray direction d, where x, hand n are obtained through interpolating with mfine. The training process consists of three steps: initialization, training feature embedding modules, and training the mesh-based neural render. The initialization of XHand model is crucial, and random initialization has a great impact on training due to estimation errors in Psi-LBS and Psi-d. The loss function during initialization is formulated as a combination of the L1 loss between the rendered image and the ground truth image, and the Laplacian terms to regularize the mesh optimization. The loss functions of feature embedding modules are designed to minimize the errors of rendering images, including the rendering loss LRGB and the regularization term LREG. The part-aware Laplace smoothing term LPLAP is introduced to reduce excessive roughness in albedo and displacement without affecting the fine details. The regularization terms are employed to conform the optimized mesh to the hand geometry, including the part-aware Laplacian smoothing terms, the L1 loss between the mask rendered during inverse rendering and the original mono mask, and the penalties for edge length changes and displacement. The proposed XHand model is evaluated on the InterHand2.6M and DeepHandMesh datasets. The InterHand2.6M dataset consists of large-scale multiview sequences capturing a wide range of hand poses, with each sequence having dozens of images with a resolution of 512 x 334 pixels. The DeepHandMesh dataset features images captured from 5 different viewpoints, matching the resolution of those in InterHand2.6M, along with corresponding 3D hand scans. The XHand model is trained on the InterHand2.6M dataset with 20 views across 50 frames for each sequence, and the remaining frames are used for evaluation. The model is implemented using PyTorch and Atom Optimizer with a learning rate of 5e-4. The feature embedding modules are firstly trained for 500 epochs using inverse rendering, and then the feature embedding modules and neural render are jointly trained for 500 epochs. The evaluation metrics used are peak signal-to-noise ratio, PSNR, structural similarity index, SSIM, and learned perceptual image patch similarity, LPIPS. The results show that the XHand approach achieves the best results with a PSNR of 34.3 decibels, outperforming other methods such as LISA, Hand Avatar, HandNA RF, and LiveHand. The XHand model also achieves 56 frames per second, FPS, on inference, with the feature embedding modules requiring 0.7 milliseconds, inverse rendering requiring 15 milliseconds, and the neural rendering module needing 0.1 milliseconds. The results on the DeepHandMesh dataset show that the XHand method outperforms the annotated mono mesh and DHM by 3.3 mm and 1.2 mm on P2S, respectively. The visual results on image synthesis and geometry on InterHand2.6M test split demonstrate that the XHand model can accurately capture the underlying hand mesh deformation and exhibit more prominent skin wrinkles based on different poses. The proposed feature embedding module and topological consistent mesh model result in enhanced rendering quality and geometry quality. The proposed XHand method efficiently drives personalized hand expressions from arbitrary hand gesture inputs, as demonstrated in Fig. 8, which visualizes the results of different identities animated using reference poses. The method's performance is evaluated using in the wild data as a reference for hand poses, with pose parameters extracted from Hamer. The ablation study in Table 3 assesses the effects of different components, including feature embedding, part-aware Laplace smoothing, and position encoding, on the model's performance. The results show that the feature embedding module and part-aware Laplace regularization significantly improve the rendering quality, while the position encoder in neural rendering leads to better image quality. The ablation study on the number of views in Table IV demonstrates the model's robustness across different numbers of input images, with competitive results achieved even with limited viewpoints. The study also highlights the importance of sufficient training data to avoid reconstruction failure. The choice of neural rendering network is also evaluated, with the proposed mesh-based network outperforming traditional neural radiance fields and other rendering methods, such as UNet and EG3D, in terms of rendering quality and inference speed, as shown in Table V. The visual results in Fig. 9 and Fig. 10 demonstrate the method's capability to generate personalized hand expressions based on any given hand gesture, with high fidelity and adaptability across various input gestures. The proposed part-aware Laplace regularization effectively reduces surface artifacts without sacrificing details, and the feature embedding modules guide the learning of hand avatars by distinguishing average features and pose features, enhancing the reconstruction accuracy. The mesh-based network eliminates the necessity for point cloud sampling, allowing for efficient and high-fidelity rendering through vertex features. Title: XHand. Real-time expressive hand avatar with photorealistic rendering and fine-grained geometry. Abstract. This paper presents XHand, a real-time expressive hand avatar with photorealistic rendering and fine-grained geometry. The proposed method leverages effective feature embedding modules to distinguish average features and pose-dependent features, resulting in finely detailed meshes with respect to hand poses. A mesh-based neural render is employed to ensure high-quality hand synthesis, utilizing part-aware Laplace regularization to reduce artifacts while maintaining details through different levels of regularization. Rigorous evaluations conducted on the InterHand2.6M and DeepHandMesh datasets demonstrate the ability to produce high-fidelity geometry and texture for hand animations across a wide range of poses. Introduction. The creation of realistic hand avatars is crucial for various applications in computer vision, robotics, and virtual reality. However, generating high-quality hand models that capture both geometric and photometric details remains a challenging task. This paper introduces XHand, a novel approach that addresses these challenges by leveraging neural rendering techniques and mesh-based representations. Methodology. XHand employs a two-stage pipeline consisting of a feature embedding module and a mesh-based neural render. The feature embedding module utilizes a UNet architecture to extract both average and pose-dependent features from input images. These features are then used to generate detailed hand meshes through a mesh deformation process. The mesh-based neural render employs a neural radiance field to model the appearance of the hand, ensuring photorealistic rendering results. Experiments and results. The proposed method is evaluated on two benchmark datasets, InterHand2.6M and DeepHandMesh. Quantitative and qualitative results demonstrate that XHand outperforms state-of-the-art methods in terms of geometry and texture accuracy, as well as rendering quality. Ablation studies further highlight the effectiveness of the feature embedding module and the mesh-based neural render in improving overall performance. Conclusion. XHand offers a significant advancement in the field of hand avatar creation, providing a real-time expressive hand avatar with photorealistic rendering and fine-grained geometry. Future work includes exploring the effective mono-model parameter estimator to further improve the accuracy and efficiency of the proposed method.